Okay, hi all. I hope you are enjoying your Good Friday holiday. Okay, so for today's video, we'll be going through this pre-WA2 practice paper. This is actually a WA2 that is set in 2023. Okay, so the topics that are tested for them back then in 2023 was thermal properties of metal. So this is really not included in our 2025 WA2. So I will be going through static, current and DC. Okay, then in the other practice paper we'll be doing light as well. So for question 1 is actually on thermal properties, so we'll just skip that. Okay, question 2, a large negatively charged metal sphere. So this is metal and it is negative and it is large. This large actually means the size of the sphere and not how much it is being charged. It is connected to a smaller size, positively charged sphere, okay, by a piece of connecting wire. Therefore, the charges will be flowing. Electrons will be going from the large sphere to the smaller sphere, whereas current will actually be going from the small sphere, positively charged, to the negatively charged. So they're asking for the true statement. So in A, a conventional current, which is our I, okay, will flow from large to the small. So this is false. Okay. B, a conventional current will flow from the small to the large momentarily. This is true, right? Because as stated over here, and momentarily is because after that they will have the same charge, right? Because they are now connected as one whole body. But however, we do not know which one is more positively charged, which one is more negatively charged. That's why it is uncertain for C and D. That's why the answer is B. Okay, unless I tell you that the large sphere is actually 2 plus or 3 plus, I give it a certain quantity. But now they are just telling us that it is net negative charge or net positive charge. So you wouldn't know how the charges will be, what it will be after they are connected. Okay, so for question 3, we have a positively charged metal sphere placed between 2 uncharged, which means neutral, and one of them is grounded to the earth. So when I put this positively charged metal sphere in between them, the electrons on the left hand side, the left sphere, will be attracted towards the right hand side. Okay, and it will stay like that. For the metal sphere that is on the right hand side, this one, okay, the electrons will also be attracted to the positively charged sphere, leaving behind the positive charges on the right hand side of the sphere. And since it is Earth, therefore electrons will actually move up to neutralize the net positive charges accumulated on the sphere. Okay, it is not going up to neutralize the protons. Okay, so I will over here it will become neutral. Okay, so I'm looking for the option of that, and the answer will be C. Okay. Question 4, how could be the unit of potential difference, the volt be also written? Now, as you know the formula, EMF or volts is equals to work done over charge. Okay, and the unit for EMF or volts or voltage or potential difference is the volts. Whereas the unit for work done is joules, the unit for charge is C. Therefore, V is also equivalent to J over C. Answer is D. Okay, now potential divider, your teacher and including me may not have finished going through the entire DC circuit. Okay, but potential divider is actually works for resistors in series only. Okay, it is working in series because of the concept that the current that's flowing in a series connection is constant throughout. Okay, so maybe I'll talk to you a little bit about potential difference. Okay, this plus 5 volts is actually at a potential of plus 5. Okay, so I will say this is a potential of plus 5. And over here will be a potential of 0. How about this 3 volts? It will be at a potential of 3. For this 2 volts, it will be at a potential of 2 volts. I'm saying it as a potential. Okay, at that point in time, what is the potential? So if I were to compare 5 volts and 3 volts, the potential difference that is over here will be a difference of 5 and 3, right? So giving me a potential difference of 2 volts. Okay, whereas for this, I will have a potential of 1 volt, and this, I will have a potential of 2 volts. Okay, so you see that this is 2 volts, this is 1 volt, and this is 2 volts. Okay, and because they have the same current going through them, therefore the resistance must take a ratio of 2:1:2. Okay, so this is R3, R2, and R1, right? So the answer will be C. You look for this ratio, 2:1:2. This is the concept of potential divider, which means the larger the potential, the larger the resistor, the larger the potential difference that is across the resistor. But it only works for series. Okay. So that's for MCQ. Section B, question 1 is on a thermal property, so we'll not be going through. Question 2 as well. This is to cut short the video. Okay, figure 3.1 shows a helicopter that's being used for a rescue mission. When the helicopter flies through the air, rotation causes the blades to rub with the surrounding air, and the helicopter becomes negatively charged. Okay, so the helicopter explained in terms of the movement of electrons. So you need to have this being explained in your answer. Okay, so explain in terms of the movement of electrons, how the helicopter becomes negatively charged. So they are telling you that the helicopter is now negatively charged. Okay, so how do we explain this? You have actually seen this in your tutorial. Similar. Okay, this is charging by friction. Let me show you the answer. Okay, when the blades rub against the surrounding air, the blades are charged by friction, okay, and therefore it gains electrons from the air. How do we know that it gains and not loses electrons? Because the question stem tells you that it becomes negatively charged, okay. And remember, for static electricity, you can only mention about the movement of electrons, okay. You cannot in your answer imply or state that protons move, okay, because that is not allowed, okay, it's not possible. Okay, then you follow up with this statement, which is actually what I talked to you all about in your tutorial. Why it becomes negatively charged, other than the movement of electrons from the air into helicopter. Now you need to say that there are more electrons than protons, okay, to end off by saying, to conclude that that's why the helicopter becomes net negative charge. Okay, now figure 3.2 shows a Van de Graaff generator. It produces negative charges which collect on the metasphere, right? So all these are the negative charges. Generator is used to demonstrate what happens when a person is charged with static electricity. Okay, so you see this person X, right? Y tries to touch him. Okay, what is person X doing? Person X is now standing on a stool placed on a thick sheet of plastic. So plastic, you will know that it is an insulator. Okay, so they ask, why is plastic used instead of iron? Of course, iron is a conductor of electricity. Plastic is an insulator. Okay, so what is the answer for this? Why do we use plastic instead of iron? So in order for the Van de Graaff to work, right, we need the charges to accumulate, right? So if this is instead of using plastic, we are using iron, right? The iron will allow the charges to flow into the earth, right? So that's why we use plastic. Plastic is an electrical insulator. You need to say this, and please add in electrical, right? Because there is also thermal insulator. In this chapter, we are dealing with electricity. We need to say electrical insulator. And this ensures that the negative charges, which they mentioned that it is on the Van de Graaff generator, it will not flow from the person X to the ground. Okay? Or you mention anything like the idea of earthing lah. Okay? Now, when person X comes close to Y, a spark is seen to form between them because there was a discharge, right? The spark lasts for 20 milliseconds. So T equals to 20 times 10 to the power minus 3 seconds. Why do I change it to 10 to the power minus 3? Because everything must be in SI unit for the formula I know. Okay. A charge of 0.0010 coulomb is passed. So this is actually my Q. I have Q and T, and the voltage is this. 200,000 volts. Calculate the amount of current. Current is I, so we use this formula. Q equals IT, and it is a SI unit formula. That's why my T must be in seconds, which is the SI unit for time. Therefore, my current will become 0.050 ampere. 1 mark for this. Calculate the amount of energy. So energy we learn from the V equals to W over Q formula. Now we have V 200,000 volts. Make sure you key in your zeros correctly. They want amount of energy, which is W. So they need our Q. Q is actually 0.0010. So in the end, your W will be 200 joules. Alright, simple. Okay, so that's why it's 1 mark, 1 mark. Okay, next. Okay, figure 4.1 shows a straight resistance wire hung from the ceiling. Okay, the resistance wire is connected to a circuit via its two ends A and B over here. Okay, and this is our resistance wire. At end A, which is over here, the mass hanger is already 50 grams. Okay, so that's how we add on more masses. So different slotted masses are placed on a mass hanger, and the corresponding ammeter and voltmeter readings are recorded, right? Ammeter, voltmeter, and this is 12 volts. Okay, so you see that the ammeter reading at 0 is blah blah blah, so on and so forth. So they want us to define electrical resistance of an electrical component. So this answer can actually be found in your notes. Okay, so make sure you memorize some of the definitions, or actually all of the definition. Okay, let me show. Okay. Electrical resistance is the ratio of the potential difference across the electrical component to the current flowing through the electrical component. Okay, take note, if they sometimes use define electrical resistance of a lamp, okay, of the lamp, then you need to change it to lamp. Okay, just answer according to the context. Now, using the data corresponding to slotted mass of 20 grams, this is important. Later we look at the data for 20 grams. Determine the resistance of the resistance wire. So if we look at 20 grams, the ammeter reading is 110 milliampere. The voltmeter reading is 11.45 volts. So this is what you need to take note of in the heading. Okay, so resistance is actually V over I. And from there, from the 20 grams data, we know the V is 11.45. Our I is actually 110 milliampere, which is 0.11 ampere, right? So we'll get a reading of 104 ohms. Okay. C. The battery has an electromotive force of 12 volts and an unknown internal resistance. Okay, which is actually a resistor found inside the battery. So inside a battery, there is also a small resistance, right, in series with the cells. So usually when we are dealing with DC circuit, right, example like this, we will not need to bother about this internal resistance. It's only when the question specifies that you need to go and find. If not, if I have 12 volts, I have 6 ohm there, you don't need to say, hey, is there any internal resistance? There is, but for our DC circuit, we are just there to analyze the circuit. Okay, so I can just say that the current is 2 ampere. Okay, but for this case, there's actually internal resistor, right? So we need to take note of it because they want us to determine the value of the internal resistance. However, they want us to use the data corresponding to the slotted mass of 40 grams, right? So let's look at how we can do this question. Okay, internal resistance of the battery is in series with the resistance wire, right? Therefore, the potential difference across the internal resistance is 12 minus 11.47. How do I get 11.47? Let's look at the 40 grams. The voltage is 11.47. So if you use 11.45, which was in part B, then your answer is incorrect. You need to use the corresponding reading. So here they specify they wanted 40 grams. So this is 11.47, we'll get 0.53. But how about the current? We also have to use the corresponding value, which is 106 milliampere. Convert it to ampere, it will be 0.106. So again, we apply V equals to IR. So my R equals to V over I. We get this value, okay, of 5 ohm. Now, as the number of slotted mass placed on a mass hanger increases, the resistance wire will be stretched. When it is stretched, the length will increase. And I'm also thinking that the cross-sectional area will decrease. So what is the formula that we are relating it to? Rho L over A, right? So the length will increase, cross-sectional area decrease. That means my resistance should increase due to these two factors. So they want us to explain the trend of the ammeter reading in table 4.2 when it increases from 0 grams to 40 grams. So I just bother with the 0 gram to 40 grams data. Okay, so let's take a look at the answer. Okay, as the mass of the slotted mass increases, the resistance wire is stretched. Okay, this is in the question stem. This increases the length of the resistance wire, decreases the cross-sectional area, right? Volume remains the same, right? Because it's just stretched. Now, resistivity of the wire remains unchanged because it's still the same material. Therefore, you bring in the formula. According to R equals to rho L over A, the resistance increases, which was what I mentioned over here. Okay, so this will increase the effective resistance of the whole circuit because I have this. Let's say inside I have a internal resistance. Then this is the wire. Okay, so if this resistance increase, effective resistance of the whole circuit will increase. And then using V equals IR, because this is 12 volts, it is fixed, the current decreases. So the ammeter reading, which they want us to explain the trend, will show a decreasing trend. And if we look at it, it actually shows a decreasing trend as we add more and more mass. Okay, so I will need you all to know this formula. This is under current of electricity. Okay, now suggest a possible reason why there's no ammeter reading when slotted mass of 50 grams is placed on a mass hanger. Really? Let's see. Okay, suddenly there's no reading, right? Possibly, actually it's because the wire has snapped and then it produces a open circuit. Okay. The wire is not able to support the weight of the slotted mass and has broken and snapped, resulting in an open circuit. That's why there is no reading. When you see the questions saying that suggest, right, it means to give a plausible answer. Plausible. Okay. Okay, question 5, figure 5.1 shows 3 identical resistors. Identical, that means they have the same resistance. The resistance of each is 15 ohms. Okay, maybe we just write it down here so we can remember. And the lamp is actually 5 ohm written over here. Calculate the total resistance of the circuit when both switches are closed. So S1 and S2 are closed. So to do this, one quick way is you redraw the circuit. Okay, so it doesn't take a very long time, but it will help. Okay, so this is 15 ohm, 15 ohm, and 15 ohm. This is 5 ohm. So actually we need to find out what is the effective resistance of this. If we have two similar resistors in parallel, okay, or if we have resistors in parallel, usually we'll use 1 over REFF equals to 1 over R1 plus 1 over R2, right? Then we do the inverse to find our REFF, okay? But however, if we have two resistors in parallel and they happen to be the same resistance, the effective resistance will be half of the resistors. What do I mean? So 15 ohm and 15 ohm, the effective resistance will then be 7.5 ohm. Okay, you can put in some values. Maybe you do 4 ohm, 4 ohm. So the effective resistance will be 2. Okay. So while I'm talking, I've already redrawn the circuit into 7.5 ohm, which was actually the parallel resistors. I combine them, they become an effective resistance of 7.5. And then they are in series with this 5 ohm and 15 ohm. So again, I'm going to redraw this circuit into something simpler. Because 7.5 and 7.5 and 5 ohm, they are actually in series, I can actually combine them. Then I have 15 ohm here. Okay, so then you ask me, hey, can you use the trick of like two resistors in parallel is equals to half of one of them? You can't, because in this case they are not having the same value. So I will need to use my parallel resistors formula. Okay, I'm just thinking that maybe some of you have not been practicing a lot, so I'll just show the working here. Okay, so I will continue to write 1 over REFF, and then I make this into a fraction. So it is 27.5 over 187.5. Okay, but this is not the final answer because I'm showing the value for 1 over REFF. I need to flip it. REFF equals to 187.5 over 27.5. Okay, and if I do my calculation, it will be 6.82 ohm. Okay, so the effective resistance is actually 6.82 ohm, and this is actually a very simple circuit, right? Because there's only one resistor, the effective resistance, right? So I'll get 6.82 ohms. Now they want us to calculate the potential difference across the lamp when both switches are closed. So they want us to find the potential difference of the lamp when both switches are closed. Okay, so to do this, maybe you can use this circuit because we have the lamp that is showing here, and this is a circuit whereby both switches are closed. Both switches are closed. Okay, so if you know this, the potential difference in parallel is actually same. That means I think just now I mentioned the idea of potential, right? So over here, this is 12 volts. The potential is 12. Over here, the potential is 0 volts. Okay, that means I have a potential difference of 12 across the battery, which is over here. Okay, now if this is a potential of 12 volts, I'm telling you this will also be 12 volts. This will also have potential of 12 volts. This will also be potential of 12 volts. So basically this whole line has a potential of 12. Has a potential of 12. Okay, this whole line, I give up. This whole line has a potential of 12. Okay, and this whole line has a potential of 0. That means across this 15 ohm, there's a potential difference of 12. Potential difference. Across this 7.5 ohm and 5 ohm battery light bulb, there is a potential difference of 12. Why? Because they are connected in parallel to this 12 volts. Alright, so across here and here will be a potential of 12, potential difference of 12. Here and here will be a potential difference of 12. Why? Because in parallel connection, potential difference is the same. So if I know this, then I can actually calculate the current that flows through this branch because I know the potential difference. So this is 7.5 ohm, this is 5 ohm. Okay, and I know from this point to this point the potential difference is 12 because it was connected in parallel to this 12 volts. So I can actually break this down into, I still keep my 12 volts, I combine them into one single resistor of 12.5 ohm. Okay, 12.5 ohm. And therefore, this is my R, this is my V. I can calculate the current that flows through using V equals to IR. My V is 12, my I is unknown, my R is 12.5. Therefore, my current is 0.96 ampere. Okay, so why do I do this? Because I want to calculate the potential difference across the light bulb. And now I know that the current is 0.96 ampere. I will know the current that flows through the 7.5 ohm is also 0.96. I know that the current flowing through the 5 ohm lamp is also 0.96. Why? Because in series, the current is the sum. Current is the same. Okay, so I have this sum. So if you know series and parallel, they are different kinds of connection, right? Okay, and you need to know this relationship. Voltage in series is sum. Current in series is same, right? Because in series, there's only one path. The current must be the same throughout. Therefore, the voltage in parallel must be same, right? Just now I already explained. The current in parallel must be sum. So this is the sum. So I hope you can write this down in your WA2 before you start so that you know what is the relationship. You need to be able to apply this. And how do I memorize this is I know that the current in series is definitely the same because there's only one path. The current flowing in must be the current that flows out, so it must be the same. So once I have filled in this grid here, right, then the voltage must be sum lah. And of course parallel must be opposite to series, so you just flip it. Okay, so I will also know that the current in flowing through this 5 ohm is 0.96 because they are connected in series. There's only one path flowing from here to here, right? So if I know the current that flows through the 5 ohm by using V equals IR, I know its current is 0.96. The resistance is 5. Therefore, I will get a value of 4.8 volts. Okay, 4.8 volts. So the answer for this is 4.8 volts across the lamp. But how about the voltage across the 7.5 ohm? Okay, let's do a check. V equals IR. I know the current flowing through this 7.5 ohm resistor is 0.96. I know its resistance is 7.5. Let's do our multiplication. 0.96 multiplied by 4.5, we get 4.32 volts. Okay, 0.96 times 7.5, I get a value of 7.2 volts. So over here is 7.2, across the lamp is 4.8, and their sum is actually 12 volts, right? Which is what we say here. In series, right, the voltage is the sum. Okay, so this is how we apply sum. Okay, there's another way to do this, and it is by potential divider. So maybe you can wait for your teacher to teach you how to do this potential divider. Okay. Okay, then question 6. A student sets up a circuit as shown in figure 6.1. I have 18 volts, I have LDR, I have my R, and I have a filament lamp. Okay, you may not have learned LDR before. LDR is actually called a light dependent resistor. light dependent resistor. Okay, it is actually in the last part of this chapter. Light dependent resistor is very special. It is a resistor, but it also depends on the amount of light. When the amount of light intensity falls, when the light intensity that is shining on this light dependent resistor is high, the resistance of LDR will be low. Okay, that means when it's sunny, I have a lot of sunlight, example, falling on or shining down on this LDR, the light intensity is very high, the resistance will be low. Okay, which means to say when it's dark, when it's nighttime, okay, the amount of light on this LDR, the light intensity is low. The resistance of this LDR will be high. Okay, so this is LDR, is light dependent resistance. So R is a fixed resistor in the circuit. Filament lamp over here is marked as 12 volts, 0.25 ampere. So this is a V, this is the I. So I can actually calculate for 12 volts and at a current of 0.25, what is the resistance of this filament lamp. But you should also know that filament lamp is non-ohmic. Okay, so the circuit is used to produce a current voltage graph for the filament lamp. So on figure 6.2, sketch a IV graph for the filament lamp. Okay, IV graph. So for IV graph, the ratio of I to V represents, okay, 1 over resistance of the lamp. Okay, so I think you have learned this, right? That when current increases, right, the lamp will heat up, the temperature will increase. This will actually increases the resistance of the filament lamp because it's a non-ohmic. Therefore, it will take on this form of, you will take on this shape. Okay, it will take on this shape. Because actually for IV graph, for lamp, you learn in your notes, it looks like this. Okay, so this is for the positive voltage, this is negative voltage. Okay, so for IV, the ratio of I to V represents 1 over R. Right, as current increases, temperature increases, the resistance increases. Therefore, the ratio will decrease, right? The ratio decrease. Next, the student shines a torchlight of increasing brightness at the LDR. Explain why the potential difference across R increases. Let's look at this. Now we have more light on the LDR. And explain just now, when it is sunny, when there's more light on the LDR, the resistance will decrease. Okay, the resistance of LDR decreases when there is more light shining on the LDR. Okay, and because R and LDR, they are connected in a series. So this one actually uses your potential divider rule, or I can try to explain using effective resistance. Okay. When my resistance of the LDR decreases, the entire potential, the entire effective resistance of this parallel branch, which is this LDR plus a filament lamp, will actually decrease. Okay. It may sound very abstract, so now I'm going to try to use numbers to convince you. Okay. So example, I have a parallel branch. Okay. Something like that. So let's keep this at 4 ohm. And this one maybe 8 ohms. Okay. So when we have 8 ohm and 4 ohm, the effective resistance is actually effective resistance is 2.67 ohm. Okay. Now I'm proposing that when the resistance of this decreases, okay, maybe it decreases to 4 ohm. So what happens to the effective resistance? When one of the resistors in the parallel branch decreases in resistance, the REFF is actually 2 ohms. You see that the effective resistance actually decreases, right? So when this LDR experiences more light, the resistance decreases. Therefore, this parallel branch effective resistance will decrease. Okay? If it decreases, what happens to the effective resistance of the entire circuit? The effective resistance of the entire circuit will decrease, right? Because now you are adding a smaller resistance here to the fixed resistor, so the effective resistance will decrease. And what does it mean? It means the current that comes out will increase. If the current comes out increases, for this resistor there is no change, but I have more current, it means the voltage across here will increase. Okay, so this is the explanation. Let me show you the answer. Okay, when the brightness of the torchlight increases, resistance of LDR decreases. Okay, this causes the effective resistance across the parallel branch to decrease, and therefore effective resistance of the circuit to decrease, right? So like what I say, the parallel branch will decrease in resistance, and the whole circuit's resistance will also decrease. And because my V is fixed, effective resistance decreases, the current that flows out will increase. And the current that flows into R, which is the fixed resistors, will increase. Therefore, the potential difference across R will also increase. We can also use a potential divider formula, which is actually in the second part of this chapter, to explain. Okay, but I think our all the teachers have not gone to this potential divider formula, so don't worry. So for the WA, right, it will only be like on a series and parallel circuit, or maybe a combination of series and parallel. So you need to know your how to get your effective resistance, how to know which circuit is being shown, is it series or parallel, and to find the effective resistance. Okay, I'll be doing another video on the next practice paper.